All right, everyone, welcome back to our second lesson with 1D kinematics. Today, we are going to be talking about distance and displacement. Okay, you guys have probably all heard of distance before, maybe some of you displacement, but we're going to be talking about this more with physics term. What do these two things mean? Okay, so distance is a scalar quantity that refers to how much ground an object has covered during its motion. So again, scalar, which we should have learned from last time, meaning it doesn't have a direction. It doesn't care for a direction. Okay, displacement is a vector quantity like this. It has a direction and it cares about the direction. That refers to how far your ending point is from your starting point. Okay, so we have a good example right here. I'm going to box it. Okay, so let's say, for example, you are starting at point A. You're starting at point A and you're taking a stroll, I don't know, through the park. And you make this kind of walk through the park and you end up at point B. Okay. The distance that you cover is pretty much how far you walked through the park and how far you got to point B. I don't know, let's just give an example. The distance you covered is going to be 300 meters. Who knows? Okay, so that's your distance, is how much ground an object has covered. Okay, your displacement, however, does not care what you did in the middle. It only cares about where you started and where you ended, how much you have displaced yourself, or how much an object has displaced itself from where it started to where it ended. Okay, and this is what we call the displacement. The variable that we use is this triangle, which we call change, and this x, which is position. So change in position, this is where you started, this is where you ended. This change in position is what we call the displacement. And let's say in this case, your distance is 300 meters, but I don't know, maybe your displacement is 50 meters. And it looks like this is coming at a certain angle, but I don't know. For now, I'm just going to say to the right. Okay. So this displacement gives us a magnitude, 50 meters, and also a direction. Okay. So let's look a little bit at this formula. Displacement is equal to the final position minus the initial position. So this triangle here, remember, that stands for change in, and this x is position. So change in position is equal to your final position subtracted by your initial position. Okay. And even if this is confusing, after doing some example problems, this should make a little bit more sense. Okay. Let's do our first mathematical example. A lion spots a baby zebra and sprints to the right. After the lion ran 45 meters, he gets sad about eating a zebra and decides to head back, moving 20 meters to the left. Okay, whenever you're doing problems like this, I highly suggest, because a lot of times students hate word problems. It's a little bit jumbles up, it seems confusing, things like that, but it's all about breaking down the problems. So let's go through this together, and I'm going to show you some tips for how to break it down. The first thing that you want to do is you want to underline key piece of information. Okay, this will help your brain organize the information better, and physics is all about organizing. So lion is sprinting to the right. Okay, I'm underlining right. That's probably a key piece of information. The lion runs 45 meters. Okay, good. He gets sad about eating a zebra and decides to head back. Okay, he heads back, moving 20 meters to the left. Okay. And the second thing is to draw out the problem. We have a little bit of a drawing here, so that's helpful, but sometimes you won't, so it's really important to draw out the problem. And you don't need to be skillful in drawing. I'll show an example. So I'm going to just draw the line here, and it's going to be a box. And then I'm going to draw a zebra here. I'm going to draw it as a circle. So this lion is running after the zebra and goes 45 meters. Gets sad and about eating it and goes 20 meters to the left. Okay, and that's all you have to draw. So something like that, and that really again helps to organize the problem. When you just read it and you're not breaking it down, it's really hard to understand what's going on. Okay, so now let's look at the part A. What distance did the lion travel? So remember, distance is just the amount of ground covered. So we should be able to know, okay, he went 45 minutes, then 45 meters, and then went 20 meters to the left. And again, distance doesn't care about direction, so we could just add everything up. He first went 45 meters, then he went 20 meters. Oh, I'm adding this meters. And then the total amount the lion went was 65 meters. What is the displacement? What displacement did the lion travel? So remember, displacement here only cares about 2 points. It only cares about the very beginning and the very end. It does not care about anything that happened in between the where it started and where it ended. So from here to here is the displacement. And maybe I'll do that in a different color. I'll do it with blue. So this is the displacement right here. Okay. Okay. So remember, displacement is equal to the final position minus the initial position. I'm going to call this position position 0. That's usually where it starts out from. And then, and I'll call that the position, initial. Ooh, I put this 0 here. Sometimes 0 stands for the initial, but I said I, so I'm going to keep it consistent, I. And then the final position we're going to call right here. And it's a little bit confusing. How we could figure this out is we could do 45 minus 20, and this is 25 meters. So we know that this spot right here is 25 meters. Okay, so now let's plug into the formula. We have position final is 25, position initial is 0, and then we can see that the displacement is 25 meters. And that would be correct. That's enough. You could just have it like that. And the reason you can have it like this and not put a direction is there's an invisible positive sign here that shows that it's positive, meaning it's to the right. However, if you don't like that, you can also put 25 meters, and this is saying to the right. It's to the right of where it started, so you can say 25 meters right. Okay, and those would both be correct. All right. Okay, next is conceptual example here. The odometer in your car, does it track the distance your car has traveled, or does it track the displacement of your car? Explain. If you want to pause it to think about it, please do so. Okay, so this is your odometer. Maybe some of you are driving, maybe you're not, but this is your odometer. And let's say if you went to the grocery store and you came back from the grocery store, what would the odometer track? So maybe not all of you guys know how this works, but an odometer tracks how far your car has been going the whole time. So if it tracks all of that, that means it's going to be tracking the distance it covers. For example, if you went to the grocery store and you came back, your displacement would be equal to 0 because you started and ended at the same exact point. So your displacement would be 0. However, your odometer doesn't track that, or your odometer tracks how far that you moved throughout. It doesn't care if you went up, down, left, right, or anything like that. It just covers how much your car has been moving. So that is the distance. Okay. Great. It will just record how much the car moved regardless of direction. Great. Okay. Jim travels 60 meters east to go to Cindy's house. However, Cindy is not home, so he decides to head 40 meters west to hang out with Harry. What distance did Jim travel? What is Jim's displacement? Okay. So again, we want to start out with underlying key piece of information, 60 meters east. Not home, so he decides to head 40 meters west to hang out with Harry. What distance did Jim travel? Again, a lot of this is drawn out. I'm not going to just draw it out, a lot of it, but I'm going to draw out what's important. So he goes 60 meters to Cindy's house. So Jim is going to start out here, and then he's going to go to Cindy's house. Boom. And this was 60 meters. He realizes he's not there, and then goes to Harry's house. From here, he goes. Boom. Okay. Again, with these word problems, important to underline key piece of information and then draw it. It just seems impossible, and you might feel really confused, but once you draw it out, once you take these little steps, it becomes a lot more possible. So just gain some confidence by doing these little steps. Underline the problem, draw it out. Just take it one step at a time, and then you should feel the confidence of being able to do this. Okay, so what distance did he travel? Again, distance does not care about direction. So we could just add everything up. 60 plus 40, and this is going to be equal to 100 meters. The next question, and I'm going to change colors for this. This part is asking for displacement. So remember, displacement cares only about 2 points. Where you started, that's the initial position, and where you ended, that's going to be the final position. Okay? And over here is your displacement. Okay. So to figure out this final, let's say, we usually often call the starting position 0. So we're going to just call that 0. And to figure out this final position here, we're just going to do 60 minus 40, and we have this as 20 meters. Okay, so displacement is equal to the final position minus the initial position, which is equal to 20 minus 0. So we're going to just say 20 meters. And again, that would be correct. Or we can say 20 meters, and this says east. They're using east, not left and right. So we're going to do 20 meters east. All right. Okay, moving on. Example 3. Cindy notices Jim coming to her house and decides to run out the door 150 meters to the east. Afterwards, Cindy goes to Harry's house, which is 40 meters to the west of Cindy's house. Okay, so again, this is where it starts to become a little bit confusing. So it's really important to use these key things. Underline the important words, and then draw the problem. Especially if you don't draw this out, you might have gotten pretty confused here. What distance did Cindy travel? Okay, so Cindy's starting here. She runs out of her house 150 meters east. And then afterwards, she goes to Harry's house. So she's going to go all the way over here. And it says Cindy goes to Harry's house, which is 40 meters to the west of Cindy's house. Okay, so let's just put this here. This is 40 meters to the west of Cindy's house. So this might have been a little confusing if you didn't draw it, but what we have is when she goes all the way back to her house, that's 150 meters. But then when she goes another additional 40 meters to Harry's house. So I'm going to call this huge green arrow here 190 meters to the west. Okay? Because even though it looks simple, if you don't draw it out, sometimes you'll make a lot of little mistakes. So again, highly recommend drawing it. Okay, part A. So again, distance doesn't care about direction. We're just adding everything up. 150 plus 190. And this is going to be equal to 340 meters. Okay. What is the displacement? Okay, again, I'm going to use a different color. Okay, let's do that. Part B. Again, displacement only cares about where you started. I'm going to call this position initial. And where you ended. Call this position final. Okay. And remember, how far you are from where you started is the displacement. Okay, so again, I'm going to call this initial position 0, and we have to figure out what this final position is. So we can find that it is to the left of where it started, 40 meters. Okay, we can kind of see that there. So I'm going to call this actually negative 40 meters here, or negative 40 for now. Okay, so again, displacement is equal to the final position minus the initial position. So this time, the displacement is equal to the final position, which is negative 40, minus the initial position, which is 0. So what this means is the displacement is equal to negative 40 meters. Okay? If you want to do it a different way, we can call it 40 meters to the west. Okay, and this would be correct. Negative 40 meters to the west would not be correct because that's a double negative and they would cancel each other out. So if you can write negative 40 meters or 40 meters to the left. Honestly, I would suggest doing negative 40 instead. This will just getting into the habit of having that negative instead of direction, instead of the written direction, will be more helpful later on. But anyway, for now, it doesn't really matter. So you could do either one. They're both correct. Okay, now let's look at this. I think this is the last math example for distance and displacement. So Jim's mom tells Jim to go buy some eggs at the grocery. On his way, Jim sees and walks up to a red penguin to the right of the grocery store. He's so excited, he forgets about the eggs and runs to Cindy's house to tell her about this. Then Jim gets a call from his mom asking about the eggs. He rushes to the grocery store before it closes, but as soon as he gets there, he passes out. Okay, a lot going on here. What is Jim's displacement? What is x? What is the total distance Jim traveled? How far does Cindy live from Jim? Okay, so a lot going on. Um, a lot of this is drawn out for us, so that's kind of nice. We're looking for x at some point, but we're looking for displacement at the beginning. So since we're looking for displacement, let's think about where we started and where we ended. It doesn't matter anything that happens in between. So I think Jim's mom tells Jim to go buy some eggs at the grocery store. So he starts at his house. Okay, we're calling this position initial, which is 0. And then he goes to the grocery store, and then he goes see the red penguin, and then he goes to Cindy's house, and then he again goes to the grocery store and passes out. So he ends right here, this grocery store. And this is the final position. Okay? And we can see that from the initial position here, it is just 200 meters away. Okay, so what is Jim's displacement? That's the final position, which is 200, minus the initial position, which is 0. So this is going to be equal to 200 meters. Does it say east or west or right? Oh, I guess it doesn't say anything. Okay, so we can just say positive 200 meters. And if you put 200 meters to the right, that'll also be fine. Okay, part B asks, what is x? So at the bottom of the screen over here, we have something x. So we know a bunch of things. First of all, we know, and let me do a different color since we're doing a different problem. Let me use the screen. We know from the grocery store to the red penguin is 50 meters. Then we also know from Cindy's house to the red penguin is 125 meters. Oops, not the best color, I guess. So we should know from Cindy's house to the grocery store, which is what x is going to be this 125 minus this 50. Okay, so x is equal to 125 minus 50, which is equal to 75 meters. Okay, so I'm just going to put this as 75 meters here. Okay, what is the total distance Jim traveled? Okay, let me use a different color. Let's do this purple. I think it's purple. So a little bit confusing. Let's just kind of read it out. He first goes to the grocery store. That is 200 meters. So with the distance, we're just adding everything up. So I'm just going to just put that right there again. 200. Then he sees a red penguin. Goes to the penguin. That's 50. So I'm going to do plus 50. He's so excited, he forgets about the eggs and runs to Cindy's house. Okay, so he goes all the way to Cindy's house. And we have that as 125 meters, so plus 125. And then he gets yelled at by his mom, and then he goes to the grocery store. And we found out that's 75. So we're just going to add all of this up. 200 plus 50 plus 125 plus 75, that's going to be 450 meters. Okay, how far does Cindy live from Jim? last part of this question. Okay, so let's use this light blue. How far does Cindy live from Jim? Okay, so what we're trying to figure out is, I'm gonna call this D. I don't know, what should I call this? X? I'll call it Y. I'll just call it Y. Okay. So one thing that we should know is that from Jim's house to the grocery store is 200 meters. But then we also know that from Cindy's house to the grocery store is 75 meters. So to figure out what this Y value is that I gave it, we just have to do 200 minus 75. And then what we get is 125 meters. Where's the total? How far does Cindy live from Jim? 125 meters. Okay. I hope that all makes sense. Again, watch it again if it doesn't. But I hope that makes sense. That's as hard as we're going to get with distance and displacement. But yeah, the rest of the chapter will get harder, but at least for right now, this is as hard it gets for the topic of distance and displacement. Okay, last question for distance and displacement. Conceptual example number 6. Can you drive your car in such a way that the distance it covers is greater than the magnitude of its displacement? B. Can you drive your car in such a way that the distance it covers is equal to the magnitude of its displacement? C. Can you drive your car in such a way that the distance it covers is less than the magnitude of its displacement? If your answer is yes, give an example for each case. If your answer is no, explain why for each case. Okay, part A. Can you drive your car in such a way where the distance covered is greater than the magnitude of its displacement? Yes. Example of that is pretty much if your car goes in any kind of a way that's not a straight line, then the distance it covers is going to be a lot more than the displacement. This displacement is dotted right here, and that's going to be a lot less than this crazy loop-de-loop thing I drew. So if it's not a straight line, it's going to be more than displacement. So yes. Part B. Let me do a different color. Do this. Part B. Can you drive your car in such a way that the distance it covers is equal to the magnitude of its displacement? Yes. Like I mentioned, if it moves in a straight line, then the distance and displacement will have the same magnitude. C. Can you drive your car in such a way that the distance it covers is less than the magnitude of its displacement? No, it's not possible. Nope. Okay. All right. Next time we're going to be talking a little bit about speed. I guess a little precursor to that. Let's talk about time. I'll let you guys think about this. Like, what is time? How can we define time? And the truth is, we can't really define time. It's not something that's really possible. Time is something that can be measured. You know, we measure in seconds and years or months, days, hours, whatever. And we can compare it. Something can be longer and shorter, but it's not really something that we can define. So time is so fundamental to our existence, that's not something we can define. However, we can still compare and measure time, like we mentioned. All right, guys, next time we're going to talk about speed and velocity, which has to do with time. And we're going to talk more about speed and velocity. Thanks for watching, everybody.